To be recording for Adrian. Darn it, sorry. Sorry, Adrian, we started early. Here we go. And then we have underneath it 4 cos 4 theta times cos theta minus sine 4 theta sine theta. And really, you can't put those together. That's trigonometry, okay? Sometimes we forget all our trig rules. But if you have different angles, you can't combine, okay? Unless you use some big fancy identities for trigonometry. We don't need that because we're specifically asked to find the derivative or the slope of the tangent line at pi over 8. So at this point, you would plug pi over 8 in for theta. So we'll plug in pi over 8 in for theta. Or in other words, we're going to find the slope of the tangent line when theta is pi over 8. And so let's see if you guys are getting that. 4 pi over 8. How did the second sign become? I probably did. Oh, it should be. That should be pi 8, not pi 2. It did because I was not being mindful and I was canceling that other one out ahead of time. Thank you for pointing that out. I appreciate that. And so you guys are canceling, right? Pi and 8 and getting 2. Pi and 8 and that becomes 2. That one becomes not 0.
Pi over 2 is cosine?
Oh, cosine of pi over 2 is 0. You're right. Yep, you're right. Cosine of pi over 2 is 0. And because it's multiplied, that's going to give us a 0 right there. Beautiful. Sine of pi over 2 is 1. And so that's going to give us a number 1. Professor Layla made these choices. And so I'm going with them. That's correct. Cosine of pi is 0. And sine of pi over 2 is 1. And so you guys should be getting down to 0 plus cosine pi over 8. Is that true?
Yes.
Over 0 minus, I messed that up. Yep, I see I have a mistake. This is sine. This is sine. It is so easy to make mistakes. So when you get your test back and you say, oh my God, why did I do that? Because it's so easy to make mistakes. What'd you guys get? Negative cotangent pi over 8?
Yes.
That guy's not on the unit circle, so I would probably, oh, that's low. I would probably, in web work, just type in negative cotangent parentheses pi over 8. Make sure you have a parentheses around that entire argument, that entire angle. It should take it in web work if that's the case. Otherwise, you can use a calculator or Desmos and get an approximation, okay? So what's happening? Sine 4 theta, if you think about it, is one of those petals, right? In fact, there should be, we did those petals, those pretty flowers, and it should have 8 leaves to it, I think, because we double it. Because you guys see what I'm saying? So it should be like a pretty flower with 8 leaves. And at pi over 8, you should see that you have a negative slope going on there. So, does anybody have any questions on your warm-up for what we just did? We wanted the slope, and we found the slope because we took the first derivative. So today what we're going to do is we're going to learn 2 new formulas, area and arc length. So this was a review from last time. But today we're going to learn area and arc length. And as a preface to area, I want to talk about how do we find the area under a curve. So hang tight. Let me just go forward a bunch of spaces. Way back when we first learned area under a curve in integration, so if we had the area under a curve, I wasn't with you when you guys learned this. What did you do to find the area under a curve? How did you develop that formula? What did you use? You divided this up into what? Little sections. Do you remember doing this? And each little section was a what? Was a rectangle. Exactly. And it was a delta x or a dx across the bottom. And then you had the height of each rectangle being f of x. And so you divided the area up into rectangles and you added all of those rectangle areas up, right? The height times the width gives you the area of the rectangle, and then you added them all up. Well, in polar, because we studied polar now we've looked at polars, all of our functions were kind of circular in nature instead of rectangular, right? So it would make sense that when you develop an area formula in polar, that you're not using rectangles anymore. We're going to be using circles to help define our area formula. Does that make sense to everybody? So somewhere in there, we're going to be using, to get the area of these curves, we're going to be using pi r squared, or a fraction thereof. So that gives us motivation to talk about the area of a polar region. My colleague made these notes. I think they're beautiful, so I'm stealing the notes from her. So you have to thank Dr. Pataki if you see her, because she did some really nice work here. But the area of a polar region can be defined as follows. And we're going to come through and get our formula. But instead of rectangles, just like you said, it's circular in nature. And so what is the area of a sector? Do you guys know? It's the area of a circle, pi r squared. Can you guys see that? Probably not, Joey, because it's so small. But the area of a sector, that's what our formula is all based on. Instead of width and length, width and height, we're now talking what's the area of one of these sectors. Well, the area of the whole circle is pi r squared. But if I want a fraction of the circle, I simply take the angle divided by 360, or the angle divided by 2 pi, and that tells me the fraction that I'm talking about. And so if I take that fraction times pi r squared, that actually gives me the area for that sector, which is 1/2 theta r squared.
Would this be like when theta is in terms of pi?
Yes, radians. We have to be in radian measure. Yes. Yes. So that's one sector. Now, what do we do to get the whole area of a thing? We take a lot of these sectors added up, and then we make those sectors get really small and thin, right? So we take a limit. And so what Dr. Pataki's notes, which you have in your calculus, in your module, I posted these, but she goes through and walks through all of these steps here of how you take your region. We subdivide that region into little sectors. And then we make those sectors, the width of each sector, shrink. So we add up, we take all these sectors, we add them up, and when you put it all together, you should see these Riemann sums coming into play. You get this formula right here, and I'm going to alter it just ever so slightly. The area, undo. The area of a polar region bounded by, and I'm going to slightly change, instead of A to B, I like to reserve A and B for XY plane, and I like to use alpha and beta to describe my angles. So the area of a polar region bounded by theta equals alpha to theta equals beta can be given by this formula right here. The area of that polar region is the integral from alpha to beta of 1/2 times the function of theta squared d theta. And again, instead of f, I always like to put r in here. And I like to put r because my functions are all r equals a function of theta. So I like to put r in there. So the area for any polar curve can be given as the integral from alpha to beta of 1/2 r of theta squared d theta, okay? Write that formula down, keep it handy, because you're going to use that formula. Well, normally I do an easier example to start with, but we're just going to jump right into the harder example, and I want to show you this. So instead of doing something that's solid, we're going to take two shapes and find the area between two shapes. So we are actually going to need one more formula. Yes. The area of a polar region between two curves is what we need. And it follows the idea of kind of when we talked about a washer, how the way you get the area of a washer is you take the area of the outside circle and then you take the area of the inside circle and you subtract them. And when you take the area of the outside circle, take away the area of the inside circle, it gives you your leftover piece. Same idea is happening here. To get the area of this shape right here, you are going to take the area of the outside, so I'll call that big R squared, minus the area of the inside, so I'll call that little r squared, where big R is our outside function and little r is our inside function. And if they ever swap, well, then you have to kind of break up your integral, right, into different functions. But I think for our purposes, I think these curves have one outside and one inside. Can you guys see and visualize this red area, right, that we're trying to get? Do you see that? And what is my outside curve, my big curve, the one that's farthest from the pole, Avery? Yeah, so my outside curve is 1 minus cosine theta. And Joey, you must see the inside then, right? Yeah. My inside curve is pretty cool. It's just, my inside curve is the radius r equals 1/2. So that's my inside theta. And so when we go to set up this integral, we're going to be taking the area inside the cardioid, outside the circle, is given by the integral from alpha to beta of 1/2 big R squared. And what did you say that is? 1 minus cosine theta squared minus little r squared d theta. Now, so I'll do what Andy said, which is I'm going to go ahead at this point, now that we have our setup, and FOIL out that piece right here. So 1 minus cosine theta squared, that was my big R, and I squared it. 1/2, that was my little r, and I squared it. And now I'm going to FOIL out that big R. So let's see. And we'll worry about the limits in a second, okay? Right now I just want to see. 1 minus cos theta times 1 minus cos theta is going to give us 1 minus 2 cosine theta plus cosine squared theta. And then 1/2 times 1/2 squared, which is 1/4, right? So I think, let me go one more step before I look for my limits. And let me distribute. I'm going to distribute. And that's going to give me 1/2 minus cosine theta, beautiful, plus 1/2 cosine squared theta minus 1/8. Oh, I think I goofed this morning because I think I wrote down something wrong this morning. Because I did not get the same numbers today, right now. Ta-da! Absolutely, thank you. I love it. I don't have to tell my class. Ta-da! I'll have to give them this thing. Absolutely. Unless I goof now. Am I goofing? Are we good? You guys are helping me. And so if I went one, and notice we haven't even stuck limits on yet, right? We haven't even put limits on yet. So now we want to put things together. What can you guys do to put together those, did you put the 1/2 and the 1/8 together? You don't have to. You could leave it separate. But I think I'll put my 1/2 and my 1/8 together, alpha, beta. And I'm putting 1/2 together with my 1/8, and that's going to give me what? 3/8? 3/8 minus cosine theta. And I'm going to set myself up here. I can't integrate cosine squared. Why not? Because it's a square, right? So what do we do for an even power of cosine and sine? We magic wave our wand and use it and turn it into half angle formula. We use power reducing half angle formula. Cosine squared, hang on, so I have a 1/2 and then cosine squared becomes 1/2 times 1 plus cosine 2 theta, right? Or 1/4 plus 1/4 cos 2 theta. I hope I did that right. I'm going to do one more step and just make it clean. 3/2 plus 1/4 gives me 5/8. Yeah or no?
You just said a half.
Sorry, plus 1/4. My bad. Somebody's going to have to check my math.
It looks right.
It looks right. You're so cute. It looks right. Let me see. 2 plus 3 is 5/8 minus cosine theta plus 1/4 cos 2 theta. Now we haven't touched our limits yet, and I'm purposely not touching our limits yet because that's tricky, okay, for students. So I'm purposely not touching my limits yet. I'm just focusing on the integration because there are some people that really are still struggling with the integration piece, and that's okay. That just means we need to work through this. How are we? Is everybody okay? So I've used my half angle identity formula, and the next step now is to take the antiderivative. Got me an antiderivative. Get me an antiderivative without even worrying about our limits yet.
I was just trying to follow.
Oh, yeah, I'm going to stop and just let you guys copy and get me some antiderivatives. Because if I keep writing, I'm just going to keep writing really fast. So I'm going to let you guys get caught up. Stop my recording. So everybody gets caught up. And make sure I didn't make any mistakes. So when you took this integral, you got 5/8 theta minus sine theta plus 1/8 sine 2 theta from alpha to beta. Is that true? Did everybody get what I got? 5/8 minus sine theta plus 1/8 sine 2 theta. Did I mess up anywhere, Andy?
How did you get 1/8 as well? Because you,
Right here?
if you multiply it by 2 and you take the derivative, that's 2/4.
Correct, but I'm not taking the derivative, I'm taking the
Integral. So that's
antiderivative. So what we're really doing, if you do it out, is you're doing, Bobby, a U sub, like you said. And when you did your U sub, did you get a half come out front?
Yeah.
And so then the 1/4 times the 1/2 came to the 1/8. Because you're doing antiderivative, it flips it over. So now we're good. Now we've done all our integration. We're happy.
And we know.
And the only thing we haven't figured out is alpha and beta. Who's got questions? So it looks like something, right? We want to go from where the two curves intersect. Where do the two curves meet? So how did we do it on the xy plane? We set a system of equations and we solved, remember? What are we going to do for this? How are we going to figure out where those two curves meet? What are we going to do? We're going to see where they meet. Go to YouTube. Oh, there you are. Set them equal to each other. Yes, sir. Thank you. We have r equals 1 minus cosine theta. We have r equals 1/2. We want those two curves to be at the same place at the same time, so we create a system of equations. Joey, yeah? That's what we're doing, 1000%. We want to equal them to each other. So I get 1 minus 1/2 equals cosine theta. I'm looking for cosine theta is 1/2. And then we have to go back to our good old unit circle, right?
Do you know the school doesn't pay for mathematics anymore?
I figured not.
We got it last year for free. I'm very upset.
Maybe they don't have the money anymore, huh?
I mean, we just lose $50 million.
You guys getting pi over 3 and 5 pi over 3? There's a lot of symmetry. So you could go pi over 3 to pi and double it if you wanted to. Okay? But we'll put pi over 3 to 5 pi over 3 on here. Pi over 3 to 5 pi over 3. So we've got area is 5/8. And I'm going to replace my limits with what we just said they are.
So you work counterclockwise?
Yes, counterclockwise, just like the unit circle, 1000%. We're going to go from pi over 3 to 5 pi over 3, or like I said, you could go pi over 3 to pi and double that area because you got symmetry. But just for now, I'm going to put them all in because it's visually, you can see that on Desmos as well. You would plug pi over 3 in everywhere. Come up with a value, and then you would plug 5 pi over 3 in everywhere. And come up with a value. And I'm running out of space. But you guys are doing this on your paper, and some people just at this point plug it right into WebWork just like this with all the symbols. And some people will work it out. I would work it out because I like math, and I would love to find sine of pi over 3, which is square root 3 over 2. And sine of 5 pi over 3, negative square root 3 over 2, and double that whole thing. And okay. when finding the area for polar curves, you have this special formula. 1/2 outside curve squared minus 1/2 inside curve squared. Yeah, and
Always moving theta, and then this will be opposed.
for polar, we're doing with respect to theta. Yep, for polar. How are you guys? You want to try one? All right, let's try one. Are you ready? Let's try one up. I am recording. I messed that up. Thank you. That is goofed. Thank you, thank you, thank you. Thank you, thank you, thank you. Good catch. Thank you so much. My first angle is pi over 3. That's my start. That's my bottom. Thank you. My bottom one is 5 pi over 3. That's the second one. Oh my gosh, thank you. So this should be 5 pi over 3 on top. This should be pi over 3 on the bottom. Thank you, thank you, thank you. Which means this quantity goes first minus that other quantity. I have it swapped. Thank you so much. Thank you. I just completely flipped it upside down. Thank you. Jake.
If you did the alpha and beta as pi over 3 and negative pi over 3, would that be inner circle, or would that be able to, would you be able to use that to get the outer? Like you said, beta to
Interesting.
negative
Interesting.
pi over 3 and then alpha to pi over 3.
Right. Interesting. Very interesting. Because, oh no, you have to be careful because your signs are different there. Your cosines match, but your sines don't. Do you see what I'm saying? So actually you would be getting that area that's in between. You would be getting,
You would be getting the outer area.
you'd be getting that is, yes. Do you see what I'm saying?
Yeah.
Yes. Yes. Okay, guys, ready for a practice? Here we go. Set up the integral to find the area inside the circle, r equal 2 sine theta, outside the circle, r equal 1. First thing you have to decide is which curve is which curve, right? You need to decide which curve is which curve. Did they tell us?
Inside and then outside your.
Oh, they told us. Ha ha ha, they told us. Inside the circle, outside the circle. But you know from last time we graphed r equals 1, which was a circle centered, well, we graphed like r equals 3, where it's a circle centered at the origin or the pole. And then we graphed that other circles. Remember, we spent time looking at 2 sine theta, 2 cos theta, 4 sine theta. That's the circle that's sitting up higher, right? So your outside curve is your big R, and that's 2 sine theta. Beautiful. And your inside curve is r equal 1. Good. So set up your integral. You want to get, and I'll just write that formula down so we have it handy. The area is going to go from alpha to beta of 1/2 big R squared minus 1/2 little r squared d theta, right? So the key is limits and integration.
Wow, that's it's great. So basically, we need a slower breakdown here.
Slow down, Gina.
Oh, okay, sorry. I'm going to slow down and stop and see how you guys are doing there. Go ahead. Keep working. If you finish, you can always look at the web work and start your web work if you finish ahead, or somebody else could bring it up there for me.
No, my brother is right. Why are we currently sitting at cosine?
Because we use
Where's your house?
integrated now.
My
brother was right.
Oh, okay, good. Okay, so that guy What is sine squared? You're going to change sine squared.
That shit literally just shattered you, motherfucker. Shouldn't it be negative cosine? You. What? Shouldn't it be negative cosine?
I don't know.
Who's got questions? Who else has questions?
Need a pencil.
I have a pencil. I'm pissed that you drove that pencil. That was my good pencil. That was your good one? Yes, it was my good one. Why is this Monday class? You leave it in my room.
This is not our normal.
That is very
I also might have this Zoom class. I don't remember. I remember you all things out of whack.
I was trying to post your list. You see what I did with the cards back?
When were you here last week?
Yeah.
I wasn't here.
Oh, you know what?
Okay, you leave your Xbox and over everything you own inside. I'm here every day.
Well,
Who got an answer, guys? See if you guys get 5 pi over 6. Is anybody getting 5 pi over 6?
No, that's stupid.
Now I respect you as an
Oh, okay.
Clearly you're not that good at math.
Dude, I'm really just trying to do that. Okay, so I got to 1.
I do actually. You don't.
It's a function in a function. For the same reason we have to
Over there. No, it's over there.
We're only confirming whether answers right or wrong.
All right.
Wrong, we don't.
What? No.
Integration technique.
Because I just like leave it. And then I just have to compare it to what we're going to Alright, so you have one
I was already signed.
How did you
That will start.
If it's no throne, you eat on all sides.
So here's what you're reading. I didn't put it. Why is it
You do that, I would find it.
because it's one of minus sine squared.
Yeah, all of us have
one half.
supposed to be just because we're trying.
So you get
1 minus a half is 1.
1/2. You bring that out. Okay.
Okay.
And you bring that out.
What is negative?
1/2 is negative. So it's negative 1/2. And then you have a positive 1. So it's 1 minus.
Let's do this out. Let's see what we get. Let's see. Because I see what time it is and we have to do arc length yet. Let's see.
There's a whole thing right
Yeah, so what I can put it into.
How's it not
5 pi over 3 is
because we have the 2
But apparently he was driving for 3 hours.
We are taking
You're taking energy,
5 pi over 3. 5 pi over 4.
I think it does.
Wait, no.
I think it definitely does.
Okay, guys, this is something you need to do. When you get an even power of sines and cosines, look back in our notes for section 7.2, and we did, 7.2, 7.3, somewhere in there, 7.3, 7.2. Even powers of sine, we turn into power-reducing formula. We get 5 pi over 6 or no? Pi over 3, okay. Hang on, let me see. Let me see. So now this 1/2 will get multiplied times this 2 in the front, and so technically it'll go away. Bobby, yeah?
Are you allowed to, when you made what do you call it, distributed the square?
Yes.
Is that not a FOIL? Shoot.
Yes and no. 2 sine theta is connected by multiplication. So technically it is FOIL, but not quite. It's using the exponent rule But because everything is multiplied, do you see? I only need a 4. Now, on test exam 2, we had to do something just like this, where we had to FOIL it. And in that case, on test 2, because it had a plus, you had to come up with 4 terms. Okay? So, it was an excellent question. That was an excellent question. Absolutely 1000% excellent question. So that gave me 1 minus cos 2 theta minus a half inside, because the 2 and the half canceled. Is this right? Did you guys do this out this way? Did you do this? Am I doing right? And did you combine the 1 and a half? I probably would put the 1 and a half together. And 1 minus a half is just a half. So this is what I would get down to. And then I would take the antiderivative, which is 1/2 theta minus 1/2 sine 2 theta. And I know I did this wrong this morning, because that's not what I got. And if you plug things in, you'd get 1/2 times 5 pi over 6 minus 1/2 times sine of 10 pi over 6 minus 1/2 times pi over 6 minus makes plus 1/2 sine of 2 pi over 6. And what does that give us? That gives us 10 pi over 12. I'm getting a 12 in here. Minus 1 pi over 12. I see it. Okay.
Should it be 10 pi? Wouldn't it just be 5 pi?
And I'm going down because people went all the way down. It is minus pi over 12. Oh, God, yes. Thank you. Yes. Plus 1/2 sine pi over 3. Huh. Sine of 5 pi over 3 is the opposite of the sine of pi over 3. I'm getting 4 pi over 12 minus 1/2 times the negative square root 3 over 2 plus 1/2 times the positive square root 3 over 2. I'm getting pi over 3 plus 2 square root 3 over 4. Now, I could very well, which is just square root 3 over 2. I could very well be wrong.
Yeah, no, that's right. That looks right.
I'm looking because I've got this negative, though. See, there's a negative in here. There's a negative in here.
I was thinking about that. Yeah, because we're multiplying a negative here times a negative square root of 2 as a positive.
I think so.
We have a plus and a negative.
I'm going to show you one more formula. So, are there any questions? Did you guys find any mistakes? Again, I'm going to send this link out so you can have this link and you can go through this video if you want to. All right? I'll email this out with a reminder about our retest days. Okay? So I'll email this out. Oh, you're in the wrong class. Sorry. But it's the same things. You guys just have different homework due. So you guys have different homework due.
That's dangerous.
So your 10-3, 10-4 is due on Thursday.
No, Buzz Lightyear.
Okay, so one more formula, guys, because I'm going to stop 10 minutes early to give you your test back. One more formula, and that is the arc length formula. It would be fun. If we had time, I want to generate this for you and explain to you how you come up with arc length, how you take little segments and we find the hypotenuse of a triangle for each segment and we add them up. But if we did all of the theory, and I'm going to switch out a couple things here, to get the arc length, when I say arc length, do you guys know what I mean? It's the length of the curve, right? If I had a circle, I'm just getting the perimeter of the circle, so 2 pi r. But for us, our arc length would be how far is it to get all the way around this curve, the arc length. So the arc length formula is this. And I'm going to do this and show you that I'm going to change my limits. So instead of a to b, we're doing alpha beta again. And this should be d theta. If you happen to have the notes and you've downloaded the notes, there were 2 typos. And f is our r value. So I would actually change this to be r and r prime. And I have to, again, thank Dr. Bataki for making these notes up. But I'm going to slightly change up her notes and put r in there and r prime. And so the arc length formula is the integral from alpha to beta of the square root of r squared plus the derivative of r squared. And again, if we had time, we would generate this formula, but we don't have time. So I'm just giving you the formula. All right, this is the arc length of a polar curve. And this is in your notes. It's in your notes in Canvas. And so we want to use that integral to find the arc length of the cardioid, you know, that heart butt shape, right? Set up the integral to find the length of the cardioid, r equals 1 plus cosine theta. And I'll get Desmos to graph it in a second here. But we are going to find the length of the cardioid. 1 plus cosine, starting at 0, going all the way around to 2 pi. To check, we say, okay, our radius is 2. That means when 2 equals 1 plus cosine theta, or 1 is cosine theta, that's our point at where I'm going to choose to start and stop. You can choose any point along the curve, but that's where I'm going to choose. Cosine theta is 1 at 0, and then again at 2 pi, and so I think that's the limits I would use. To get the arc length, I would go 0 to 2 pi. I'd throw my radius in there and square it. And Bobby, this is where you're going to do the FOIL. 1000%. This is where we would do our FOIL. And then I'm going to take my derivative. Hang tight. What's my derivative? Derivative of 1 plus cosine is going to be just sine. Nope. Negative sine. And so I'm actually going to leave this as an exercise for you guys to try if you want to try it. Bobby pointed out you want to FOIL this guy because there's a plus in here. We're going to FOIL him out. And then you guys are seeing, oh, hello, look, 1 plus cosine, 1 plus sine squared, cosine squared. That's just 1. And so that's just giving us 0 to 2 pi. Now, Dr. Bataki says not to integrate this, so I'm wondering if they don't make you integrate this on WebWork. If we were to integrate this, it's a cool thing. You'll notice you can't do U sub because there's no sign, so we can't do U substitution. So instead, what you actually need, if you love math, is you're going to use that power reducing formula, but you're going to use a different version of it. So if you love math, This is another trig identity that you would use to finish if you had to finish. But I'm not sure you guys have to use that because it says do not integrate right here. So I'd have to go look at your web work to see what they turn out to be, okay? Okay, we did so much today. You guys probably have